This one you might have already heard about before. And if you have, it's very likely that you have through one of these headlines like the ones that you see here. Maybe you think it's bonkers. Maybe you think you chalked it up to a conspiracy theory. Maybe you think governments are already doing it. Maybe this is the first time you hear about it, which I hope so. But in general, what I want to do today is give you my own perspective on this, the perspective of a scientist, a climate scientist that has been working on this topic, on geoengineering, for almost 10 years now. Let's start from the basics, okay? Why would we even be thinking about this? Well, we now have multiple ways to measure the impacts of human emissions on climate. One of them is this one. You can see here what we call the radiative energy imbalance of the planet. This we can measure with satellites. NASA does it every day. We know that these greenhouse gas emissions are trapping energy. They're preventing energy from escaping the planet. And so this imbalance is growing. And it's growing. Since we've been measuring it, now we are at over 1 watt per square meter of imbalance. That means a huge, if you imagine how many square meters there are, you can imagine how much that is. And the planet has to warm in response to this. And we also know that this warming is now causing increased risks across the board. These might be heat waves and fires. It might be things that have affected you or people you know already. And really, there is no other way except halting emissions and preventing more greenhouse gases from building up into the planet to prevent this imbalance from getting worse and to make sure that risks don't really get out of hand. But in the meantime, this is turning out to be so hard, and it's turning out to take time. So in the meantime, what do we do about this energy imbalance? How do we reduce it without waiting a full century? How do we stop also increasing climate risk from distracting us from doing what we actually need to know? We can't have more trees if fire weather increases and these trees are just set up on fire, right? So, and it's also clear that the impacts of climate change are also actually astounding climate scientists as well. Are things happening at a faster pace than we expected? Yes, probably. So while it will be incredibly necessary, fundamental to reduce emissions, this is really might not be enough. It is really not looking good, at least for the next 30 to 50 years. So then the question becomes, are there ways to slow down this from happening? How do we prevent these changes from overwhelming us? And yes, it turned out that they might be. The way we scientists like to call this is increasing planetary albedo. That is, reducing the energy that is coming in the planet in the form of solar radiation by reflecting a little bit of that. Now, sea ice, snow, a lot of things in the planet already do this, but their extent is going down. So then the question becomes, are there artificial ways to do this? And people have proposed multiple things. People have proposed from the smallest things, you can paint your roof white, you can make crops a little bit brighter, you can increase the albedo of ice, you can do a lot of things. A lot of these things are very local, and they might reduce local heat stress for sure. They might actually work, a lot of them, but they're not global. And climate change is a global problem. So then the question becomes, are there global ways to do this? Of course, the most global of them would be, let's put mirrors up in space. What about other things? Well, one of them is what we call stratospheric aerosol injection. That is the idea of putting aerosols in a part of the atmosphere, the stratosphere, that is way, way, way high above our heads. Not even planes fly there. And the question is, can we put stuff up there? Now, why would we have this idea? Well, the scientists have been discussing this for now over 4 decades. Paul Crutzen, he was a Nobel Prize in chemistry for his fundamental work in essentially saving us all from the ozone hole. And in 2005, he wrote this paper where he said that SAI might be the solution to the policy conundrum. That is, risks are going up, emissions are going up. What do we do in the meantime? Now, Paul Crutzen was probably one of the best atmospheric scientists around. He knew his stratospheric chemistry. He was under no impression that this was a silver bullet. He didn't think this was just going to turn back the clock. He knew that there were going to be risks. And so do I. But he thought that it was worth looking at this more because he really thought that this could have been a solution. And so do I. So now what I want to do is sort of tell you more about what the actual science tells us about this. Now, the first thing is, we know that aerosols in the stratosphere would cool the planet. We have volcanic eruptions that in the past sometimes have cooled the planet for more than a year sometimes. This has happened whenever these volcanic eruptions that threw stuff up in the stratosphere had a lot of sulfate in them. This sulfate would turn into sulfuric acid particles and reflect sunlight. So we know that this would work. The last time this happened was Mount Pinatubo erupting in 1991. We were perfectly capable of observing both the size of the particles, where they went, how long they stayed, and what impact they had. As an example, right, we can see here, the first plot that you see here is sort of what we call stratospheric optical depth. How thick is the layer of aerosols and what fraction of sunlight it reflects. 0.1 of optical depth roughly reflects 1% of sunlight. And that was able to maybe cool the planet by 0.3, 0.4, 0.5 degrees. Is not that easy to tell, but that's roughly what we know. The other thing that we knew or able to observe out of this was where the aerosols went, and the aerosols didn't stay forever. Stuff that you put in the stratosphere stays longer than it does in the troposphere, but not forever. And after 2 years, all of the aerosols were gone. So the other thing that we know, and we know well enough, is what we call the stratospheric circulation. This is a plot of that. Essentially, we know that depending on where we put stuff in the stratosphere, air will slowly mix it up longitudinally and make sure that it's pretty well mixed, but also move it towards the pole. This is very useful because then we know that depending on where we would put this stuff, the aerosols would go in different places and have different impacts. For instance, one of the things that we know is that if we were to put it in only one location, the aerosols would preferentially cool that location. That's the red line that you see here, cooling some places and not the other. But we also know that if we were putting these aerosols in multiple locations, we could have sort of a uniform layer, right, acting as a planetary shade and preventing some of the sunlight from reaching the surface. So we know that there are ways in which, if we manage to do this uniformly, it could reduce risks across the board. But this also means that we know that if we were to put the aerosols only in one location and just cool something but not the rest, that could produce more risks. And finally, we know that, of course, the climate system is incredibly complex. We know that there would be multiple interactions at what we call trade-offs. For instance, one could say, of course, these aerosols would affect stratospheric chemistry as well. That's where ozone is produced. What impact does that have on the amount of ultraviolet radiation that reaches the surface? That could be a problem. How about precipitation? Maybe it reduces the increase in precipitation coming from climate change, but what if it shifts precipitation patterns? Well, this is the point. The point is that we need to fully understand what the entire range of these trade-offs is. And the only way to do that is through climate modeling, because we're not doing SAI right now. The only way to study this is through climate modeling. Now, this is a result that you see here from maybe 6 or 7 climate models that ran this experiment all together. But currently, there are probably 100 climate models around that are used to understand the impacts of climate change. And we're not using all of them for SAI as well. A lot of people don't really want to think about this. How much more we could learn, how much better could we define our trade-offs if we were using all the full amount of science that we have? The other thing is that we also don't have data from controlled releases. Right now, we have to use what we have, which is mostly the few volcanic eruptions that happen. But what if we could have small-scale outdoor tests where we could measure things in a reliable way and figure out better where the uncertainties in our models are coming from? Now, there's a lot of reasons to be skeptical about outdoor experiments for sure, but there's so many things we do every day that release way more aerosols than what we would actually do in a release test, in a test like this, and yet we're not doing it. Finally, the last point that I want to make today is this is not just about the physics and the science. Of course, this is a complicated issue, and also SAI is never going to be a perfect solution. But we live in an imperfect world, which means that to understand what SAI could do, we don't only have to ask climate scientists or physical scientists, but we also have to ask natural scientists, social scientists, people working in humanities, everyone. Everyone needs to be involved. We can improve our climate models as much as we want, but if we don't build trust and reliability for our results, nothing's going to change. So if you come out of this talk, I don't want you to make up your mind about SAI. I don't want you to be sure there is a solution or to dismiss it. You could be excited or maybe you're doubtful. Every reaction is okay. What I want you to be convinced about is that we need way more research on this and that we need all hands on deck. We need governments to pay attention and fund research. We need private individuals and philanthropies and people interested to help fund what governments want. We need people to discuss this in a meaningful way. And we need institutions at the global level to talk about this and figure out whether we could use this. Imagine yourself 25 years from now. Maybe a lot of the other solutions that people have been talking about, maybe they will work. And 25 years from now, we've managed climate risk perfectly. And that would be great. But what if we haven't? What do you wish you would have known, or you would have started to build now in order to make the meaningful, difficult decisions that we will need to make in the future? That's what SAI research is all about. Thank you.
Well done.